You can have renal pyramids, minor calyx, major calyx, and then renal pelvis. Essentially, minor calyx, major calyx, and renal pelvis are the small chambers within the kidney that become progressively larger, and in the renal pelvis, when urine accumulates in the renal pelvis, it then drains into the ureter. Okay? So we can actually extend it into the ureter, and then urinary bladder, and then urethra, and then out. Okay? This sequence, does that make sense? So you go from renal pyramid into the minor calyx, into the major calyx, into the renal pelvis, into the ureter, urinary bladder, urethra. Okay? I'm reminding everybody, I am recording this session. Okay? All right. Good. Which one? Okay. Now, the main functional unit of the kidney is called a nephron. So, what is a nephron? And I will try to do kind of color coding here. So those are going to be blood vessels here. Okay, those are glomerular capillaries. Okay, so that's efferent arteriole. This is afferent arteriole. And those are glomerular capillaries. I'm going to call them GC. Are you following me so far? So blood goes this direction. It gets into the glomerular capillaries through afferent arteriole, and it leaves them with the efferent one. So far, we good? Now, filtration occurs in the glomerular capillaries, and fluid gets filtered into so-called Bowman's capsule or glomerular capsule. Okay? So this is glomerular capsule. From the glomerular capsule, filtrate enters proximal convoluted tubule. So proximal convoluted tubule. From proximal convoluted tubule, it enters nephron loop. So that's nephron loop. From nephron loop, it gets into the distal convoluted tubule. And from distal convoluted tubule, the filtrate ends up in the collecting duct. So far, I'm looking at so the screen where I can see your faces is here, the camera is here. This is why it's kind of weird. Does this make sense? The structure, okay. So the filtrate to filtrate will go in this direction. This way, and this way. Collecting ducts, they're not a part of the nephron. That is not a nephron, okay? Nephron ends here. Collecting duct collects the fluid from multiple nephrons. Okay, so what happens where? The filtration happens here. And in this part, happen processes of absorption, so reabsorption, and secretion. Does that make sense so far? The stuff that we put here. Make sense? Just nod if it does, and just do this if it doesn't. Okay? Nod if it does, do this if it doesn't. So, what is filtration, reabsorption, and secretion in terms of the direction of the movement of chemicals? So, if we say that it's a blood, okay, and this is filtrate, then during filtration, number one, the stuff goes from blood to filtrate. During reabsorption, from filtrate to blood. During secretion, from blood to filtrate. Okay? So my best analogy, one of my favorite ones that I use when I explain difference between filtration, reabsorption, and secretion. Imagine that you decide that you have too many things in your walk-in closet, and you decide to go a full Marie Kondo on your walk-in, okay? And you take everything and you throw everything away. That's filtration. Then you realize that you actually have nothing to wear, and you start pulling clothes back in your walk-in closet. And you pull back, you take back almost 99% of what you just filtered. Katie, can you hear me? Can you see? What cannot you see? Oh, it's too small. That's what you're saying. Okay, I have a solution for it. Move the cursor on the WebEx into the upper right corner of the screen, like here. Okay? There should be different views. Choose, what's that called? Presenter's view. Did you find it? Works for everybody? Okay, awesome. Sorry, I always forget because it's kind of, We're good? Okay. So during reabsorption, you take stuff from the filtrates back into the blood. And then in the secretion, it's a final step when you look at the clothes, nah, I probably don't need that thing, and just throw it away. So mostly drugs are secreted, okay? Some unwanted stuff. So I want to highlight a couple of things. You see this afferent arteriole, you see this efferent arteriole. You see how afferent is much bigger than efferent, much wider? See that? Because of that, the blood pressure in this structure, blood pressure in the glomerular capillaries is unusually high. Okay? So that's kind of a unique structure that it's a unique capillary bed. It is supplied by the arteriole and it is drained by the arteriole. Now, last question that I wanted to address. So these efferent arterioles, what do they form afterwards? Well, it turns out that this arteriole winds up around this nephron loops, okay? Forming what is called a peritubular capillaries. And this is where reabsorption happens, as we already mentioned. But this picture gets really, really loaded. And I wanted to address first the process of glomerular filtration. Everyone's okay? Doing all right? It's all recorded, remember. So what happens in the glomerular filtration? Well, you have blood. And you have filtrates. So blood exerts two pressures on the fluid. The hydrostatic capillary pressure, HPC, forces the fluids out of the blood into the filtrate. The osmotic capillary pressure forces the fluid, pulls the fluid back from the filtrate into the blood. We already learned about that osmotic pressure. It is driven mostly by albumin in the blood. Finally, fluid that accumulates in the Bowman's capsule or glomerular capsule is forcing fluid back in the blood as well. And this is, we call it A3GC, where GC refers to glomerular capsule. Okay? So, we're good so far? Doing all right? Okay. So, so-called net filtration pressure, or NFP, will be an equivalent of like a sum of those forces, considering that they have a direction. So, capillary hydrostatic pressure minus capillary osmotic pressure minus glomerular or capsular hydrostatic pressure. So here's the thing. If you look at this, so net filtration pressure must be positive for the filtration to occur. Does that make sense? So this parameter should be more than both of this together. Now, osmotic pressure is not really regulated. Your albumin concentrations are more or less the same all the time. Pressure inside of the renal capsule is not really regulated. It's more or less the same all the time. The only pressure that can be changed is capillary hydrostatic pressure. Okay? This is basically your blood pressure. So when blood pressure increases, net filtration pressure increases. When your blood pressure goes up, you produce more filtrate. When blood pressure decreases, the net filtration pressure goes down and you produce less filtrate. In fact, when your arterial pressure reaches 60 millimeters of mercury, it's pretty low. Your blood isn't filtered altogether, which is not good, as you can imagine. Okay? So far, you following me? So what is filtered? I'm going to say it. What is filtered? Water, ions, glucose, urea, nitrogenous wastes. Small molecules are filtered because they fit between so-called food processes of podocytes. What is not filtered, what is not going into the future urine, are red blood cells, any cells, or proteins. Large molecules stay in the blood. So far, we good? Essentially how filtration occurs, and I'm going to show it. So imagine that those are podocytes, and my fingers are food processes. So food processes, they come together like this, and the gaps between them are called filtration slits. So chemicals small can get through the filtration slits. Chemicals that are large cannot. Okay? Now, once you threw everything away, you start to reabsorb things. So how does reabsorption work? This is a pretty fascinating process, which I bet you will find very familiar. So here's the bloodstream. So this is blood in peritubular capillaries. These are cells, columnar cells, of the tubular epithelium. So it's renal, epithelium. And the filtrate is here. So what happens? Well, first, sodium ions are pumped outside of the, so that's sodium, and it is sodium-potassium pump. So sodium ions are pumped from the renal epithelium into the blood. This pumping keeps sodium concentration in the renal epithelium low. Since sodium concentration in the renal epithelium is low, and it's lower than the sodium concentration in the filtrate, sodium is diffusing into the renal epithelial cells. So it's facilitated diffusion on the apical side and active transport on the basal side. Now, you may remember the concept of, it's very similar to the absorption in the intestine. So remember, we were talking about secondary active transport, where you have diffusion of one ion facilitating active transport of another compound. And one ion, in this case sodium, goes from its high concentration to low concentration. Another ion or compound, such as, let's say, glucose, gets through the apical side by the secondary active transport. Okay? So essentially, it's a diffusion of sodium at the apical side that provides energy the glucose reabsorption from the intestine. No, from the intestine, from the filtrate, okay? And then on the basal side, glucose will use facilitated diffusion. Let me go over it one more time. Sodium-potassium pump keeps the concentration of sodium in the renal epithelium low by constantly pumping sodium into the bloodstream. Due to this, sodium constantly diffuses from the filtrate back in the epithelium. That diffusion here serves as the energy supply for the reabsorption, for the secondary active transport of glucose, amino acids, calcium, a lot of other ions from the filtrate into the epithelium and into the blood. Does that make sense so far? Does it? Okay. You're so tiny, you're so small that it makes it hard to see. Okay. Now, that's what happens with the glucose and other. Now, what happens to water? How is water reabsorbed? Turns out, water reabsorption is driven by osmosis. So water follows sodium and gets reabsorbed via osmosis. When water is reabsorbed from the filtrate, the concentration of ions in the filtrate starts to increase. Let me say this statement one more time. When water is taken out of the filtrate into the blood, the filtrate concentration increases. Does that make sense? Since it increases, ions can basically diffuse between the cells. This is true, for example, for magnesium, which can be reabsorbed by diffusion from the highly concentrated filtrate. Now, do you need to know all the reabsorption routes for all different ions? The answer is no. What you must understand first, the role of sodium, that it is actively transported out of the epithelium on the basal side and then diffuses into the epithelium on the apical side. You must understand how sodium here is important for reabsorption of glucose, amino acids, and other ions. You must know that water is reabsorbed by the osmosis follows sodium. You must understand, here's the thing, do you see those arrows running through the cells? This is called transcellular reabsorption. So ions have to cross the apical membrane, the cytoplasm, the basal membrane. You see that purple arrow going between the cells? This is called not transcellular, but paracellular route. Paracellular means cells are not involved. Am I clear? Okay, good. And so here's what we're gonna do. I'm gonna say what secretion is, and then I'm gonna politely ask you to give me like 3-minute break, okay? Okay, so reabsorption kind of makes sense. Okay, what is secretion? Stuff goes from the blood into the filtrate, that's it. Good? Like, I'm not asking any details about the secretion, not much. Okay, we got it? Okay, give me 3 minutes. Things that I wanted to discuss. Okay, got this. Okay, what I want to talk about is glomerular filtration rate, intrinsic and extrinsic controls. And that's probably going to be it. Okay, so glomerular filtration rate. Okay, what is it? It's the volume of urine. Sorry, not urine. My bad. Volume of filtrate formed per minute. Can Amanda or Ashley or Katie do me a favor? I don't really care who. One of you, can you unmute yourself for a second and say something?
Yeah. Can you hear me?
Yes, I can hear you. I just hope. Okay, excellent. Thanks. You can mute yourself again. Perfect. Because it's just easier when I put Elise on how to say it.
I'm done. I can hear you.
Oh, okay, awesome. That's good. So when I ask you, does it make sense? And I need to look at your tiny little faces at the bottom. Okay, awesome. I hope that makes sense. Normal glomerular filtration rate is 125 mils per minute. You can probably figure out at this point that I'm not asking you to memorize this number. God forbid. Okay? Now, what does that mean, like normal? If your blood vessels in your glomerulus, if they are obstructed in some way or blood flow to your kidneys is insufficient, the amount of blood that reaches your kidney will start to decline, which means you're going to start producing less and less filtrate, which means every minute you filter less. Does that make sense? It's important. Do you understand? You got it? Understood? Okay, awesome. So, what are intrinsic versus extrinsic controls? So, extrinsic controls their function is to maintain the blood pressure. Intrinsic controls maintain GFR. So intrinsic controls are essential when everything is normal, when your blood pressure is normal. Now your blood pressure fluctuates, it changes a little bit from time to time, okay? And the role of intrinsic controls is to maintain the constant normal GFR amidst those slight changes. If your blood pressure is altered in a significant way, it is very, very high, but usually it's not the case. Or it is very, very low, then extrinsic controls will dominate intrinsic. They will basically trump the regulation of GFR to maintain the blood pressure. Does that make sense? So basically, this works when everything's normal, and this works when blood pressure is too low. For instance, you're terribly dehydrated or after the blood loss. So we already discussed renal mechanisms that regulate blood pressure. One of them was direct mechanism, remember? High blood pressure leads to higher net filtration pressure, increased urine volume, which leads to decreased blood volume, which leads to decreased blood pressure. That's the direct mechanism. And the indirect mechanism will be the renin-angiotensin-aldosterone system. When low blood pressure activates renin, renin activates angiotensinogen that into angiotensin 1. Angiotensin 1 is activated into angiotensin 2. And angiotensin 2 stimulates aldosterone. Okay. Aldosterone stimulates sodium reabsorption, which stimulates water reabsorption, which increases blood volume and blood pressure. So this is the sequence. Again, low blood pressure triggers renin. Renin activates angiotensinogen into angiotensin 1. Angiotensin 1 is converted into angiotensin 2. Angiotensin 2 stimulates aldosterone. Aldosterone stimulates sodium reabsorption. By osmosis, sodium reabsorption leads to water reabsorption, and water reabsorption increases blood volume and blood pressure. Does that make sense? Okay, good. Now that's indirect mechanism. Now we kind of figured out extrinsic controls. Let's talk about intrinsic controls instead. Two mechanisms that contribute to the maintenance of the GFR. So first mechanism is myogenic mechanism. So in the myogenic mechanism, it is really pretty straightforward. So let's say your blood pressure suddenly increases. It doesn't matter whether it increases or decreases. Okay. Actually, you know what? Let's do decreases and just more physiological. It works for both ways, but decreases just kind of more relatable. So blood pressure goes down, not by much, maybe 10 millimeters of mercury, something like that. Okay. So when blood pressure goes down, it also decreases your GFR. Does that make sense? We mentioned that. Okay. So when blood pressure goes down, the stretch in arterioles also goes down. So arterioles aren't as stretched, so mechanical stimulation goes down. Now that stimulates mechanoreceptors, and mechanoreceptors cause local response. Afferent arterioles dilate, okay? Efferent arterioles constrict. So imagine that the arterioles that are going into the glomerulus become bigger. Arterioles that drain the glomerulus become smaller. This will increase blood flow to the glomerulus. This will inevitably, hold on a second, and this will inevitably increase GFR. Does that make sense? So again, when blood pressure goes down, GFR goes down. But Stretch in arterioles reduces via mechanoreceptors. It is sensed, and in response to this, afferent arterioles dilate, efferent arterioles constrict. This increases blood flow to the glomerulus, and increased blood flow to the glomerulus increases GFR. If you want to model what happens when blood pressure goes up, you just need to flip all the arrows and flip here. So in response to increased blood pressure, afferent arterioles will constrict, efferent will dilate. Does that make sense? Okay. Now, probably last thing for today, I guess, will be the concept of tubular glomerular regulation of the GFR. Yeah, we're going to talk about one other thing on that side. So this is going to be the conversation about so-called tubular glomerular mechanism. It has a lot of steps, which we will figure out together. Before we talk about those steps, I want to highlight something. So, turns out that, imagine that this is a glomerular, afferent arteriole, I'm sorry. Okay? This is proximal convoluted tubule. So it turns out that there are some cells there. So here in the proximal convoluted tubule, we have so-called macula densa cells. Okay, here. In the afferent arteriole, we have special cells. It's a smooth muscle cells that are called, not all of them, but some of them are granular cells or juxtaglomerular cells. And here in between, there are mesangial cells. I'm going to be using this image to illustrate what happens when blood pressure, what happens, how GFR is maintained constant. When blood pressure, for example, rises. So when blood pressure goes up, GFR goes up as well. Does that make sense? Now, this is going to have a lot of steps, so I'm going to check with you on each and every step to make sure that we are together following, okay? Does that make sense? So when blood pressure goes up, the filtrate volume initially also goes up. So you start making more filtrate initially. Does that make sense? Katie, Ashley, Amanda, Elise? Anisha. Okay, good. When you start making more fluid, and this fluid goes into the same system, the same pipes. When there's more fluid, the rate of filtrate flow also increases. You know, you can see it every time there's a rain outside. If rain is kind of there's not a lot of water flowing through the gutters. If rain is massive, amount of water and the speed of water, the velocity of flow through the gutters will be much higher. So rate of filtrate flow goes up. Now, since filtrate passes through proximal convoluted tubule much faster, it actually decreases reabsorption time. So basically, it leaves less time for the ions to get from the tubule, from the filtrate into the blood. Think of it this way. If you are on the train and you need to jump from the train on a platform, if the train goes slowly, you have plenty of time to do so. If the train goes fast, the time that you have to jump is much less. Does that make sense? Good. Since reabsorption time decreases, the amount of sodium that returns back in the blood goes down, and the amount of sodium that stays in the filtrate goes up. So sodium in the filtrate increases. Concentration of sodium in the filtrate goes up. Then it's pretty straightforward. Macular dense cells sense it and send the signal to the mesangial cells, to the granular cells here. Granular or juxtaglomerular, same name. And in response to that signal about increased sodium concentration in the filtrate, granular cells, remember those are smooth muscle cells. Afferent arteriole constricts. I'm going to use the down arrow to mark constricts. And efferent arteriole dilates. Constriction of afferent arteriole and dilation of the efferent arteriole will altogether decrease the glomerular flow. So glomerular blood flow will go down. And since glomerular blood flow goes down, glomerular filtration rate goes down. So let me go over this process one more time. When blood pressure increases, GFR increases as well. So when it increases, more filtrate is produced. When more filtrate is produced, filtrate moves through the tubules much faster. That fast movement of filtrate to the tubules actually decreases time for reabsorption of sodium, since not all the sodium that is supposed to be reabsorbed is going into the blood, a lot of it stays in the filtrate. So the concentration of sodium in the filtrate increases. Increased concentration of sodium in the filtrate is sensed by macular dense cells. Mesangial cells convey that signal via gap junctions through the macular dense cells to the granular and juxtaglomerular cells that surround the afferent arteriole. In response to that elevated sodium in the filtrate, afferent arterioles constrict, efferent dilate. That decreases glomerular blood flow and decreases initially increased GFR. In order to describe the same story, okay, in order to describe what happens when blood pressure is low, all you need to do is to just flip all the arrows. Does that make sense? Good? Okay, now the last part that I wanted to illustrate is the concept of transport maximum and renal clearance. So first, let's talk about transport maximum. I'm still kind of struggling with how to explain it in a graphic way better. Basically, what it means is that, remember when we talked about reabsorption, going back from the filtrate into the blood, we mentioned that many compounds, like glucose, they have to use transmembrane proteins. Is that understood? So there's a certain limit on how much of a particular chemical can be reabsorbed over a given time. You can think of it this way. You are in the room, okay? All of you are in some kind of room, and I guess this room has a door or some other opening. So imagine that I ask you, can you have people coming into your room at the rate of 1 person a minute? Sure, right? 10 people a minute? Probably so. I'm not saying where those people go, just going through the door. If I ask you, can you think of, like, can your door hold a pace of 1,000 people a minute? Probably not, right? Only, I don't know, like, well, 60 maybe people a minute can get through the door, right? Something like that. And then it doesn't matter how many people are on the other side, there is some maximum of the return. Does that make sense? That's basically the idea of transport maximum, why it is physiologically relevant. So imagine that this, so I'm going to call it scenario 1, okay? That's the amount of glucose, and it's all going to be glucose. So that is filtered amount of glucose. Okay? That's your reabsorption capacity. Okay, so that's the how much glucose was filtered from blood into the filtrate. This is how much glucose you can return in a given time. Does that make sense to you? Okay. So if your reabsorption capacity, if your transport maximum, okay, so that's your transport maximum, is much higher than your, or just higher than the amount filtered, then what you're going to have reabsorbed? Everything, right? Okay, so everything that is filtered is reabsorbed. Am I clear? Okay, so let's play a different scenario. You go to an epitome of American cuisine and lifestyle, which is Cheesecake Factory, and you buy 2 gigantic cheesecakes, and you eat them all, and your blood glucose immediately skyrockets. Are you following me so far? So this is amount, and it's a free filtration, so that is filtered. Okay? In the meantime, this is your reabsorption capacity. Remember, your reabsorption capacity, your transport maximum does not change. So, how much you're going to reabsorb? As much as your transport maximum allows. Does that make sense? And what's going to happen to the rest? Oh, the rest is going to be excreted. Does that make sense to you? Good? So why I say that it's physiologically relevant. So in case if you all are healthy and you eat these gigantic cheesecakes and your blood glucose shoots up, okay, then your blood glucose like really goes up, like this, okay, you reabsorb a whole bunch of glucose back in the blood, but that stuff will end up in the urine, and your urine will be kind of sweet, okay? It's even more relevant for people with diabetes, because if a person has poorly controlled diabetes, and this person's blood glucose is really elevated, like this, and only that amount will be reabsorbed, okay? Does that make sense? Only that amount will be reabsorbed, and the rest will be excreted with the urine. Am I clear? So that's actually, that used to be a legitimate diagnostic test to try urine, to taste it, or to put it on the windowsill. Just, yeah. It's sterile fluid. I mean, it probably doesn't taste great. Never tried, but or you can put the urine into a cup, put it on the windowsill, and see if flies are attracted by the glucose. Okay? So far, we good? The last bit of information for today is going to be renal clearance. Okay? It can be confusing, but it really is not. So renal clearance is the parameter that is measured in milliliters per minute. Which explains how fast a particular chemical is removed from the blood, or how effective it is removed from the blood. Basically, it tells you the volume of blood that is cleared of the particular chemical in 1 minute. And we always compare renal clearance to the GFR. So let me explain. First, let's call it renal clearance, just RC for the brevity, okay? So if renal clearance is equivalent to GFR, what does that mean? It means that the chemical is freely filtered no reabsorption or secretion. Does that make sense to you? So for instance, if you go to a physician and they do your urinalysis, the urine test, and one of the lines there is going to be creatinine. Creatinine is the product of protein catabolism to some extent. And creatinine is freely filtered. It's not reabsorbed. It's not secreted. It's just freely filtered. So by measuring the renal clearance for creatinine, you can clearly see if your GFR is fine. If creatinine renal clearance is 125 mils per minute, your kidneys work perfectly fine. Now, what if renal clearance is 0? And that can happen, that's totally normal. Fully reabsorbed. No secretion. Okay? For instance, in healthy patients, glucose, it has renal clearance of 0. So all glucose that is filtered it is filtered, all that glucose is fully reabsorbed. All of it is brought back into the blood. We good? And last two scenarios, one is when renal clearance is more than, well, let's hold on a second. So renal clearance is more than a 0, but less than GFR. Okay, so in between. It means it's partially reabsorbed. So, yeah. I mean, some drugs, maybe so. Okay. So some of the chemical is returned from the filtrate, but not all of it. And finally, what if renal clearance is more than GFR? Okay. Then it means no reabsorption, filtration and secretion only. Which means it's true for some drugs, which means the drug is fully filtered, and on top of that, some of it is secreted. For instance, as far as I remember, for penicillin, it is true that renal clearance is more than GFR. So let me go over it one more time and begin. So renal clearance equivalent to GFR. Chemical is filtered, there's no reabsorption, no secretion. Renal clearance equals 0. Chemical is fully reabsorbed, there's no secretion. If renal clearance is less than GFR, obviously above 0, the chemical is partially reabsorbed. And if the renal clearance is more than GFR, then it means chemical is not reabsorbed, it is filtered and secreted. Does that make sense? We're good? Good? Okay. Let me stop the recording.